Okay, let's do 7.11. We're asked to rank in order of increasing energy for three different wavelengths and colors of visible electromagnetic radiation. Now remember, what we're going to need to get at here is the energy of single photons of these different colors. Okay, the energy of a single photon, this is again a single photon in joules, is equal to Planck's constant times the frequency. This is not the wavelength, it's the frequency. Now we're given wavelengths in this problem. We know that wavelengths are inversely proportional to frequency. As the wavelength gets bigger, the frequency gets smaller. Okay, so I would pick out the biggest wavelength, 660 here, the red light, and I'd say in energy, that's the smallest, because its frequency will be the lowest. And then alternatively, I could pick out the blue light and say, oh, its energy is the highest, because its frequency is the highest. And then this one is going to be in the middle. Okay, so that's going to be basically this highest energy, this one's next, and then this one. Okay, blue light is more energetic than yellow, and red is the least energetic of them all by virtue of this equation and the frequency dependence. Now, before I finish this problem, though, I did want to talk about this a little bit more, because another thing I'd like you to do in this chapter is get an idea for how wavelength correlates with color. In this particular example, we're given three different colors, blue, red, and yellow, and then some numbers that correspond to the wavelengths of this light and what color we might perceive. So I wanted to expand upon that a little bit. Now, the visible spectrum, this is the light that we can see, extends from about 400 to 700 nanometers in wavelength. That's all that we can see, this 300 nanometer wide band of electromagnetic radiation. Of course, the spectrum, the complete electromagnetic spectrum, is much, much wider than this. This is the light that we can see. So let's talk a little bit more about that. Now, what I've done to try to explain is I've come up with a scale here from about 400 to 700 nanometers. This is the biggest wavelength. This is the smallest. This is my wavelength scale. To the left, or lower wavelengths, that's where I get into the ultraviolet, and if I go to higher wavelengths, that's where I get into the infrared, or the near infrared and mid-infrared, okay? So infrared over there, and UV at shorter wavelengths. Now this in this narrow band, that's what we can see, all right? So how does wavelength correlate with color in that narrow band? And that's what this figure is basically meant to show, okay? So down near 400, we've got our violets and our blues. Okay. Now as we proceed up to about 480 nanometers or so, that's where I start to perceive a blue-green color. So I'll call that teal. It's kind of like aquamarine, sort of a nice blue-green mix. Once you get up about 480 or so. Okay. Now once you get to about 500, you pass that a little bit, maybe 510, 520, 530. All the way really up to 545, 550 nanometers. So this whole range from about 500 to 550 or so, that's what I'm going to perceive as a nice green color light, okay? That's a very green color. By the time you get to about 570 nanometers, the color that I perceive really rapidly changes into a yellow, okay? This transition for me, it's very rapid between the green, the yellow, and the orange, and into the red. It's really only about a 50 nanometer wide band where it goes from green to completely red. So about 570 for yellow, maybe you get up 585, 590, you're into the oranges. And then by about 600 nanometers for me, I usually start to perceive that as a red color, and I do so all the way out through about 700 nanometers. This entire 100 nanometer block of wavelengths, I don't know if it's me or what, but it's very hard for me to tell those colors apart. I see them all as just a red color, okay? So I noticed that, they give 660 a red color. I would certainly perceive that This 595, maybe I would see that as like an orangish color. I'm not even sure if I actually would see that, if I would see it as orange or more red, but I probably wouldn't see it as yellow. I guess I'd see it as more orange. But this one at 453, I think I'd see that one as blue. Okay, so this is how wavelength correlates with different colors that we can see. So, one thing you can do to it's hard, I guess you have to kind of remember the different wavelengths and how they correspond, but if you want to remember this Roy-G-Biv business, right? Red, orange, yellow, green, blue, indigo, violet. This end down here is the low wavelength, and then this end over here is the higher wavelength. It basically allows you to put the colors in order of their wavelength, and then hopefully you can do that for energy and frequency as well. The energy and frequency would just kind of be reversed in terms of what's low and high. But again, this is an important learning objective for the chapter.